Hi everybody, it's Mr. Duffy. Welcome to our physics lesson for today. And today we're going to be talking about an equation that relates force, mass, and acceleration. Now, from our Pivot Interactive activity that we did on Monday and Tuesday, you should already know the relationship between force and acceleration is a direct relationship, a linear relationship. And the relationship between mass and acceleration with a constant force is going to be an inverse relationship. And so what we're going to do is we're going to just put that together into an equation that is commonly represented, again, called Newton's second law. And so we're going to do that, and then we're going to do some example problems with that, and again, some harder ones eventually we're going to work our way into. So let's go ahead and get started on that. So Newton's second law is sometimes called the law of second law of motion. Sometimes called the law of force and acceleration, because again, it relates force, mass, and acceleration. So now, the acceleration of a body is directly proportional to the net force on it and inversely proportional to its mass. We found that out again in our Pivot Interactive. But if we represent that in an equation, normally it's represented with this force equals mass times acceleration, or F equals ma. That is the way it is also on your equation sheet as well. It is important to know that the force there is the net force on the object. It's not an individual force, it's the net force. You can rearrange this as well. Acceleration equals force divided by mass, or mass equals force divided by acceleration. Since there's only three equations, and I don't normally do this, but again, you can. I normally just solve it algebraically, but you can represent it with a triangle as well. Okay, so when you have three variables here, if we cover up force, it would be mass times acceleration. If we want mass, we cover up mass, and it'd be force divided by acceleration. And again, if you cover up acceleration, it's force divided by mass. So again, that is possible to do, although not necessarily necessary. So here's again another example of this. If we are pushing with a small force, we get a small acceleration. If we push with a large force, we get a large acceleration. So again, the picture on the left, we've got one person pushing the car. On the picture on the right, we have three people pushing the car. So more force equals more acceleration. That's a direct relationship if the mass stays constant. Again, that was part one of our Pivot Interactive there. Again, the fan speed, you could vary the fan speed more or less, but if there was more force, you got more acceleration. Kind of should make sense there. So anyways, where the lesson kind of comes into play, again, we kind of learned about the relationship, the concept of the relationships on Monday and Tuesday. But in today's assignment, I'm going to be working through some of these math problems. We have simple math problems in which case, it gives us the force or mass and we just solve for the acceleration, like this problem. Or again, it might give us some other variables. So anyways, whatever I start off with, I'm gonna, like any physics problem, I'm gonna start off by writing what's given to me in the problem. The first thing it gives me, it says Roberto and Laura are studying across from each other in a wide table. Laura slide the 2.2 kilogram book, so that's the mass of the book, towards Roberto. If the net force in the book during the push, sorry, not Newton's, F, if the force equals 1.6 newtons, what is the acceleration? Okay, so again, we don't normally, but we can just definitely do this. We have our triangle, mass, and acceleration. If we're looking for acceleration, acceleration is going to become force divided by mass. So acceleration equals my force, which is 1.6 newtons, divided by our mass, which is 2.2 kilograms. And again, if I pull that up, my calculator real quick right here. If I pull that up, 1.6 divided by 2.2 is 0.7 meters per second squared. That is our acceleration. There we go. Done. Question number 2. The net force on the golf cart is 390 newtons north. If the cart has a mass of 270, what is its acceleration again? Real quick. Acceleration is force divided by mass. Force is 390 over 270 kilograms. So not really anything too much different than the last problem. We're still looking for acceleration. And so 390 divided by 270 is 1.4 meters per second squared. Okay, let's look for something different. Now, in this problem, it gives us the force and the acceleration. It asks for what is the mass of the ball. A soccer ball is kicked. What is the mass of the soccer ball? So again, the force here in the problem is 13.5 newtons. The acceleration it gives us is 6.5 meters per second squared, and we want to figure out the mass. If that was the case, mass equals force divided by acceleration. And so our force is 13.5 and our acceleration is 6.5 meters per second squared. Okay, so 13.5 divided by 6.5. Let's just say 2.1. 2.1, and the units for that would be kilograms. Okay. Now, let's go ahead. Okay, in these harder problems, what we're going to be doing is still applying Newton's second law, F equals ma, but we're going to apply it to other equations that we learned in Unit 1 with kinematic equations. So, in this first problem, a sports car accelerates from 0 to 60 miles per hour. So that would be 27 meters per second, and it does it in 6.3 seconds. The car exerts a force of 4,106 newtons. How massive is the car? Well, okay, so F equals ma, Newton's second law. It gives us the force in the problem, 4,106 newtons. And we're trying to solve for mass. That's our question mark. But what it does not give us, it doesn't give us our acceleration. It gives us our initial velocity, 0 meters per second, or even 0 miles per hour, but it's still 0 meters per second, and our final velocity, 27 meters per second. It also gives us the time that it does that over, 6.3 seconds. Now, again, it doesn't really come out directly and say this, what is the acceleration, but we should be able to find it using kinematic equations. Final velocity equals velocity initial plus acceleration times time. We have all the other pieces of information from this except for the acceleration. So we have the final velocity, 27, equals initial velocity 0, plus acceleration, which we don't know, times 6.3 seconds. Okay? So we can definitely solve for that acceleration, then use that to solve for the mass of the car. So let's go ahead and do that. Basically, it amounts to doing 27 divided by 6.3, and we get an acceleration of 4.28 or 4.29. So if our acceleration is 4.29, and now we need to plug that into F equals ma, trying to solve for mass, so that'd be force divided by acceleration. Our force is 4,106 newtons, and our acceleration we just found to be 4.29. We can divide those to find the mass. 4106 divided by 4.29 equals an acceleration of 957. Sorry, not acceleration, a mass of 957 kilograms. That is our answer. Okay, awesome. Now, let's do another one. So, in this problem, again, what we're trying to incorporate here is kinematic equations from the past. So, another problem, we got an F-14 airplane is taking off an aircraft carrier. It is actually catapulted off the deck to make it speed up really super fast. The plane's final speed at takeoff is 68.2 meters per second, and it starts from rest. The plane accelerates in 2 seconds and has a mass of 29,545 kilograms. What's the force coming from the catapult? Or actually, the jet engines too. Okay, but anyways, basically it kind of amounts to the same type of problem as the previous problem, except for we're looking for force this time. We have the mass of the airplane, 29,545, and the acceleration, we don't know. Doesn't come out directly and say it in the problem, but it does give us the velocity initial, sorry, the velocity initial is 0, starts from rest, it says that in the problem. And the final velocity it gives us is 68.2 meters per second. Okay, so we have the initial, final velocity, and then we need the time that it takes to do that. It says it takes 2 seconds for the airplane to take off. Now, this problem is very similar to the last problem, so what I'm going to do is I'm going to let you guys do that, and then I'm going to put the answer on the board so you can check your work. Okay, very similar to the last problem. Okay, so after solving that problem, very similar to the previous problem, we find an acceleration of 34.1. We plug that into F equals ma to find the force. We get a force of basically 1,000,000 newtons, which is extremely large force. But it kind of makes sense. You're accelerating such a large mass to very high speeds. This is actually very similar to how the top throw dragster actually works too. It catapults the car up the hill and so forth. So again, similar concept, but very large forces involved. Okay, so this is our final F equals ma Newton's second law problem. But you can see that it's actually lots of problems altogether. But this kind of encompasses a lot of the stuff we've already talked about in this unit. Kinematic equations, which we covered previous units, F equals ma concept, and also drawing free body diagrams and resolving like net forces and so forth. So this is all in this question, and kind of, again, good question to kind of end on. So here's what it says. The car is being pulled with a force of 10,000 newtons. The car's mass is 1,267 kilograms, but the car covers a distance of 394.6 meters in 15 seconds. I don't know why this car is being pulled. Maybe it's broken down. Who knows what the exact situation is. But okay, so it's being pulled. We want to figure out lots of different things. What is the expected acceleration from the car with the force given? What is the actual acceleration using the position and time information? What is the difference in the acceleration? Why is there a difference? And what is the magnitude and direction of the force that caused this difference in accelerations? So again, this kind of represents what we kind of see as different ways to solve for accelerations using Newton's second law, but then also using kinematic equations. And then we can kind of see, what those forces involved, what might be going on. So the first part for part A really is just an application of Newton's second law, F equals ma. We're looking for acceleration, so that's going to be force divided by mass. Now, the force given to us in part A is a 10,000 Newton force, and the mass of the car is 1,267 kilograms. So to figure out what the expected acceleration from Newton's second law is, all we have to do is divide those. So 10,000 divided by 1,267 gives us an acceleration of 7.9 meters per second squared. Okay, that's part A. Now, part B. Part B says, what is the acceleration from the position time data? Well, okay, what information does it give us here? It gives us a distance of 394.6 meters, that's our distance, and a time to do that of 15 seconds. Okay, now, I'm assuming here, and I guess it doesn't necessarily say it, but we're going to assume it starts from rest. The velocity initial of this car is 0 meters per second. I know it doesn't explicitly come out and say that in the problem, but I'm going to assume that's the case, because otherwise we can't solve this problem. So if that's the case, then we can use an equation. The distance covered equals velocity initial times time plus half at squared. We have the distance that the car moves, the displacement, and we have the initial velocity and time, so we can definitely do that. So 394.6 meters equals 0. That's going to cancel out. Plus half the acceleration, which we don't know, times the time of 15 squared. Okay, so let's go ahead and do that. 15 times 15, 225. We're going to do half that. And then we're going to do 394.6 divided by 112.5, and we get an acceleration of 3.5. Wow, that's quite a difference in accelerations. So from F equals ma, we get acceleration of 7.9, but according to our kinematic data, we're getting an acceleration of 3.5. Letter C, what is the difference in it? What's causing the difference in accelerations? So, letter C is what is the difference? So we're just going to subtract those two. 7.9 minus 3.5. 4.4 meters per second is the difference in accelerations. But letter D is what is causing that? And it has to be friction. Friction must be causing this difference in accelerations. So this difference in accelerations has to be from it could be air resistance or, rolling or sliding friction, but it's definitely from friction. Now, what is the magnitude and the direction of the force causing this difference in acceleration? So, what is the friction force, basically, is the concept. I think that would be helpful if we kind of have a free body diagram. So, if we have a free body diagram, we have the force normal of the car being pushed up from the ground. We have the weight of the car being pulled down by gravity. I'm going to assume the force is to the right, but I don't necessarily know that. A 10,000 Newton force to the right caused by the force applied, or it's being pulled. So let's maybe say it's being pulled. So let's say a tension force. There is a force to the left, but we don't know that force. It's a friction force. We don't know what that force is. And that's what this question is asking. What is that friction force? Well, that friction force is, again, causing that difference in accelerations. And so we can apply that using F equals ma. The friction force here is going to be the mass times the difference in accelerations. Or I could do this differently. Again, there's other ways to do this problem. I could solve for using the acceleration from the position time data, and then that would be the net force, basically, and then I could use that net force to solve and subtract from 10,000. But again, using the difference in accelerations is also going to do that exact same thing. So the mass of the car is, I gotta go back up, 1267 times the difference in accelerations, which was 4.4, and that's going to be the force of friction there. The friction force is causing that difference in accelerations. And so (1267) times 4.4 is giving me a friction force of 5,775 newtons. Okay, so the friction force, 5,575 newtons here. That is our free body diagram. I think that answers the question, number 7. What is the magnitude and direction of the force causing the difference in accelerations? If the object's moving to the right, friction force is to the left. So hopefully this video helps explain Newton's second law, but also helps you see some of the different problems you can encounter using Newton's second law. Some of them, again, are fairly easy, just with 3 variables. If it gives you force, mass, you can solve for acceleration. But you can see that it does get harder if we apply some of the kinematic equations from earlier in the year into these problems. So thank you very, very much for watching, and hopefully this was, again, helpful to you.